how to interpret an expression, a program in a certain context. And we have discussed two styles in the last class. I hope the presentation is visible. We are on slide 24. So the first style was the style of operational semantics, which primarily focus on an abstract machine and tries to interpret the input in terms of certain term rewriting rules, transformational rules, to get to a point whether no further transformation is possible. And we say that that is the semantics of the of the given expression. This is typically what the compilers do. Of course, they use a different vehicular language for doing that, which is often the assembly language of the target processor. The other style that we saw was axiomatic style, which does not try to do transformations. Rather, it gives certain equivalence rules or properties, the properties that must be satisfied. So based on this set of axioms or properties, we express the entire semantics of the program. This makes it easier. This makes it amenable to automated analysis, particularly for the purpose of theorem proving, for the purpose of trying to prove if programs are mathematically correct and so on. The third style, we will compare these styles at the end after we introduce the third style, is what is our main focus of discussion in this module, or in fact in this course, is that it is called the denotational semantics. The denotational semantics is a system that provides a denotation in a mathematical domain for each string of the language. So it has to rely on certain mathematical domain which are predefined and denotes that string in that domain. So far in the operational or axiomatic semantics, I mean, we are continuing with the Boolean numerals example. When we treated numeral 101, we treated it simply as a string. We said that we are not making a interpretation that this could represent natural number. In denotational semantics, we are going to do that. We could denote it to mean something very, very different. For example, we could just denote 101 to mean that it is a string of ones and zeros. But let's say one way to denote would be if we say that 101 represents the natural number 5, then formally we say that the denotation of 101 is 5. So we need, naturally, this looks like there needs to be a mapping. There needs to be a semantic function which takes strings from the language that I'm trying to give semantics to and maps each one of them to a value in the domain in which I'm expressing the semantics. So in this case, let's say the semantic function is a function M, which takes whose domain is B, that is the strings of binary numerals, and the codomain is N, the set of natural numbers. So this is called the semantic function. So this function actually tells me what the semantics is. Now, for making the notation clear, let me tell you that every semantic object, for example, here I'm trying to denote the semantics of elements of B, or in particular 101. Every semantic object is written within a double a double pair of square brackets to make it explicit that whatever is contained therein is an element of the domain that I'm trying to interpret. So to write that the denotation of 101 is 5, we will formally write M, the semantic function 101, that is an element from B, is equal to 5 in this syntactic object notation, right? So this is the basic way we are going to take a look at. So now in terms of this semantic function, we can say the semantics of B onto the natural numbers can be represented as M of 0 must be 0. Please note that both of them are written as 0, but they mean different things. On left, the 0 is a binary numeral that I'm trying to interpret. On the right, it is a constant in the natural number. Right? So you should be clear about. So that is specifically the, I mean, to disambiguate this kind of situation is specifically the reason we use the specific syntax of the syntax for the syntactic objects. Similarly, M of 1, interpretation of binary numeral 1, is the natural number 1. Then interpretation of a binary numeral x 0. So if you pad x with a 0 on the right, then it is 2 times 2 is the natural number. Multiplication is a natural number multiplication, 2 times the interpretation of mx. So we know left shift and padding with 0 basically doubles the number. So we are stating that rule. And then we say if we pad it by 1, then it is doubling plus adding 1. This is natural number 1 to that value, which is double of the interpretation of x. And finally, in terms of the binary numeral addition of x with y is interpretation of x, interpretation of y. These are two natural numbers and doing a natural number addition for them. So this is what we say is the semantics of the binary numeral with respect to the semantic domain, which is natural numbers, right? So as in the previous case, let us try to, see certain equivalent semantic interpretations. So I'm trying to derive the semantics for 101, binary numeral 101, binary added with binary numeral 111. We will show that that has an interpretation which is 12. And we will also show that the interpretation of 1100 is also 12, right? So which is very easy. I mean, this is simply written in a different way. This is just, as you can see, is a recursive definition of binary to decimal conversion as we commonly know, but seen in a very different context. So M101 matches with the rule 4, right? So there's a 1 at the end. So it matches rule 4. So I say it is twice of M10 plus 1. Then M10 matches with rule 3. So we say that this M10 is twice of M1. And then M1 matches with rule 2, which say M1 is 1. So I get this expression in the natural number domain, which I assume is already known to me, in which I'm interpreting, and I evaluate this to get 5. In a similar manner, I do the M111, which obviously gives me 7. In a similar way, I do M1100, first apply rule 3, then again apply rule 3, then apply rule 4, and then apply rule 2 to get 12. So we can see that now finally, if we do M101, M of 101 plus binary plus of 111, then according to rule 5, it is M of 101, natural number addition of M of 111. So which is 5 plus 7, which is 12, which is same as M1100. So this is basically the denotational semantics based denoting the binary numerals with the reference to the natural number set is what we get. There are, longer examples. These are just for your practice. Of course, this is too elementary. I know. There are more to. So the earlier one on slide 27 was actually showing that 12 plus 10 is 22. In slide 28, it shows 13 plus 9 is 22, and so on. So you can easily understand and do this. Certain properties that hold, I will state them without proof, and I will expect that you will work out the proof. For example, the leading zeros do not affect the value of a binary numeral. Right? This is what we are saying is a consequence of our semantic definition. For example, if I have 00101, then it denotes the same natural number 5 as 101. So in general, what you need to prove is that for any binary numeral x, a leading zero does not affect the interpretation m of 0x is m of x. Right? I will leave this proof on to you. All that you need to do is to use an induction on the length of x, and in this induction, the rightmost binary digit could be either 0 or 1. So you take two cases, and then you proceed on that induction to show that eventually this M0x can be shown to be mx. Please work it out for yourself. If you have difficulty, ask us. You can also show that the operational semantics is correct with respect to the denotational semantics, which means that operationally, if I transform a certain binary numeral, so it is a state execution process, right? It's term rewriting. So I'm taking a binary numeral with zeros, ones, and number of maybe plus operations. And then using the rules of the operational semantics, we transform it into a simplified binary numeral. So you'll have to show that the operational semantics is correct with respect to the denotational semantics. So it will, and it is easy to show that. All that you need to show is every transformation rule is correct according to the denotational semantics rules. Further, you can show that the axioms of the axiomatic semantics are logical consequences of denotational semantics. That is, if the way the denotational semantics has been given, if you follow that, then the axioms, the denotation of left-hand side and right-hand side of every axiom will match each other. So denotational semantics could lead to the axiomatic semantics as well. The question, of course, remains is, can you do the reverse? Please try to think over, answer these questions. This will give you a much better understanding of the three styles of semantics that we are talking about. So denotational semantics in general takes a more abstract view of the meaning. Instead of just going through a sequence of machine states, the meaning of a term is taken to be some mathematical object, right? So that makes it amenable to a lot of formal analysis. So it is typically a number or a function, things like that. And giving denotational semantics for a language, therefore, consists of first finding a collection of semantic domains. For example, in this case, we chose the set of natural numbers as a semantic domain. And based on that, once we have the semantic domain or a number of semantic domains, it's not necessary that one semantic domain would be enough to express the denotational semantics. We will need multiple semantic domains, and it is usually a challenge to identify these semantic domains properly, which are assumed to have an interpretation which is known to us, right? It's known a priori. Once we have that, then we have to define the interpretation function M, where maps the strings of the given input language in terms of the elements of this domain, like the rules that we did for binary numerals. As I said, the search for appropriate semantic domains for modeling various language features is given rise to a complete, full-blown theory known as the domain theory, and it relies significantly on lambda calculus, which will give us a lot of benefit advantage in understanding, because we have now mastered the lambda calculus and its different semantic styles and typing and so on. So let me just go back and ask if there are questions up to this point. Then I can answer. Otherwise, I'll go ahead and go deeper in the denotational semantics. Any questions, friends? No, it must have been very easy. So let me go back. So I mean, these are some exercise that I leave for you. Of course, many of them are not trivial, but as we go through these later parts, you'll find that you will slowly be able to write the denotational semantics for these typical data structures, for which, as you know, that writing operational semantics is not that difficult, the transformation rules. In terms of axiomatic semantics, we have already seen examples, for that matter, in case of stack, and you're supposed to work out the rest. So keep this in mind, that this is what you will need to write. Try it from time to time. That way you are able to write the denotational semantics for these cases. So to summarize on the on the semantic styles, the three semantic styles that we have discussed, let me highlight again that operational semantics tells us how to execute a program. It gives me the rewriting rules, the transformation rules, or the states of the machine that the input string has to take us through. But it does not tell us either the meaning of the program or the properties it may possess. It's just saying that, okay, do this, do this, do this, do this, kind of. And that's exactly what your compilers often actually do. It just transforms into another program. So it says, okay, in input, if you are asked to do for, then in the output, you are doing this go to, check, come back, and so on, right? But it does not try to understand the meaning of the program or any properties that it might possess. Axiomatic semantics, in contrast, describes the properties that the program must have. We have seen, for example, for stack, a whole lot of properties of empty stack, of the axiomatic way of stating what is LIFO. That is, if you push and immediately pop, you get back the original stack. If you push and then do top, you will get the element that you have pushed, and so on. But it does not say what the program means either. It just says that these are the properties, and neither it says that how to execute it. It is not operational. It is just behavioral in terms of the axioms that I have provided. Denotational semantics, in contrast, tell us what the program means, because I'm using a set of semantic domains. Like in terms of the binary numerals, neither operational semantics nor axiomatic semantics told me that I want to think of the binary numeral string 101 as natural number 5. This was not there in those. We just told us how to transform it when we add it with, say, a binary numeral string 111, or it told me axiomatically as to what property the addition must satisfy. But in denotational semantics, we are using other semantics domain to know what the program means. But in contrast, it does not necessarily tell us how to execute it. It may in a certain way, but it does not tell us how to execute it. So if we can summarize on a matrix of different semantic styles and the different characteristics they have, that whether the style gives you the meaning of the program, whether it gives you the properties that the program must satisfy, or whether it gives you a way to execute it on an abstract machine, then you can easily see that the operational semantics gives you execution, axiomatic semantics gives you the properties, and denotational semantics give you the meaning. Others are not there. So of course, so that means that in practical sense, we will possibly have to use a mix of these semantic styles, but we'll come to that later. Let us go ahead and develop on the denotational semantics more. Now, certainly when we have to talk about the semantics in general, we need the syntax. So I'm on slide 35. There are typically two ways to represent semantics, represent syntax. Suppose I'm talking about a string 4 star 2 plus 1. Now, how do you parse it? So it could be done in terms of a crisp, compact, abstract semantics. So I can just describe this syntactically, saying that an expression is either a numeral, wherein what I'm meaning is 4 is a numeral and is an expression by itself. Anything that has a value is actually an expression. 2 is a numeral and therefore an expression. 1 is a numeral and therefore an expression. Or if I have two expressions and I operate on them, I get a new expression. So 4 star 2, 4 is an expression, 2 is an expression. Operating them with operator, these are the possible 4 operators with operator star, gives me a new expression. And then I have expression, I have 1 as another expression, I do plus another operator, I get another expression. So simple recursive definition, it is ambiguous because it does not tell me whether to combine 4 with 2 first to do the multiplication and then add 1, or to add 2 with 1 and then multiply the result by 4. It does not tell me that. So it is ambiguous in terms of this abstract syntax, but it is compact to represent. On the other hand, we can have a concrete syntax, which is unambiguous, but concrete syntax necessarily becomes verbose. So what we do in terms of the concrete syntax, we are grouping the operators in two groups, low operator and high operator. So this means that these are higher precedence operator and these are lower precedence operator. And then if you look at, this will be trivial for those who have gone through the compiler course, because this is the most running example within the course, but those who have not can look at it in this way, that at the lowest level, we have factors. That is, a number is a factor, right? It is kind of the most basic unit to build an expression. And then we make a term by first applying a higher order operator between a term and a factor, or a factor itself can be treated as a term. So 4 is a factor, 2 is a factor. So I can treat 4 as a term, and I can apply the term 4 high operator star factor 2 to get 4 star 2. Now you can see that as you proceed from here, there is no way that you can treat this plus at the beginning, because it is a low order operator. Now, once you have got a term, then you can treat the term as an expression, or an expression could be an expression, a low order operator plus or minus another expression, right? Or actually, you can write this as term, and you should write this as term. Okay, so this is, in this way you make sure that star or divide, multiply or divide will always have higher precedence than plus or minus. And this string will always mean 4 times 2 and 1 added to it, not the other possible way. So concrete semantics makes it unambiguous. You can draw only one Peirce tree given the concrete syntax. I'm sorry. But the abstract syntax makes it keeps it ambiguous, but it's compact. So what we'll use in practice in denotational semantics is often we'll make use of the abstract syntax and assume that there are certain external ways to remove the ambiguity, which typically what many compilers also do. Those who have done compiler theory will know how to disambiguate an ambiguous specification in terms of using the precedence and associativity of operators. So we will often use abstract syntax because it is more compact and easy to express. Right? Now, once the syntax has been defined, then the next thing we need to define the semantic domains, right? Because we will need the semantics domain known a priori to be able to able to do the denotation. So how should we define the semantic domains? So semantic domains are typically sets associated with the operational functions. So they form the semantic domain. So they could be any collection of numbers, persons, sets, almost anything that you want to use. So some of the common sets are natural numbers, integers, rational numbers, where the numerator and the denominator are integers, but the denominator has to be greater than 0, and they are taken to the reduced form, which means that P and Q do not have a common factor between them. The greatest common divisor, or GCD, of PQ is 1, and then X is written as P by Q. So this is the rational numbers. You can have real numbers, any point on the real line. It could be characters, it could be truth values, booleans, true or false. So these are some of the common sets that we know. We have to slowly develop more on them. So based on this, the domains, now this by itself does not give me the domain, because I still do not know what operations can happen in this domain. So we will elevate these to the domains. So let me tell you how to do that. But before that, let us note that there are primitive domains like natural number, like Boolean number, Boolean values, or floating point numbers. These are absolutely known a priori. Then there are compound domains. That is, given 2 or more domains, we can build new domains. Right? So these are done through domain builders. You have seen this in terms of lambda calculus significantly, but they are just in a little different light. So there could be product domains. If A is a domain, B is a domain, A cross B, the Cartesian product is another domain. It could be sum domain, disjoint union we have talked of. I'll explain that more again. Or it could be function domain, that is A maps to B. Right? So these are the very common domain builders, where given a domain, given 2 domains or 2 or more domains, I can build a new domain. We introduce a new concept of a lifted domain. Lifted domains are domains which has a special value written in this way, like a pole on the ground called bottom. That denotes no value at all. Now this is a very extreme concept that you introduced. So where you say that I have a bottom and I can have it in any domain I want, what it means, it is no value. Or why do we need it? Because we need it typically for denoting non-termination. That is, we know that all computations may not terminate. So there are two very related concepts. One is that of an error, and one is that of a no value. An error is something which is means that the computation has actually terminated and produced something that is invalid. And non-termination is no value, that is the computation itself has not terminated. You know that is quite possible. And therefore, it has produced a no value. Now, at times, error may also be represented by this bottom, but oftentimes we will separate bottom and error and probably have both, that my termination, my computation could terminate and produce an error, which I know is an error, or my computation may not terminate at all. So if we have a bottom, then it allows me to actually have support partial functions as well, right? What did we talked about partial functions earlier. These are, we say something is a function in contrast to a relation. Something is a function if every element has a unique mapping. That is, no element maps to two other elements. But a second property of the function is, do all elements in the domain have a mapping at all? Now, often we use functions where all elements in the domain has a mapping, and we call these as total function. But it is possible to deal with domains where all elements may not have a mapping to the codomain element. So these are called partial functions. So for such, what we can say, we can model every partial function as a total function where all elements in the domain that do not map to any element in the codomain are taken to map to bottom. Right. So it means that given this, I do not know what result will be produced. No result will be produced. So there's no value. So that's the importance of having this bottom. It makes things theoretically robust, uniform, and so on. So any domain can be lifted. And if you do that, then you write is as a post subscript of that domain. So if A is a domain, then lifted A, written in this way, is A union the bottom value. Bottom value can occur in any domain. It is a unique value which can go with numbers, with strings, with anything. That's the kind of assumption, because it's actually a no value. So often A union bottom is used if I need a lifted domain for the computation. So these are my basic kind of types of semantic domains and constructions that I can have. So let me go to the next. The product domain, you already know, it is a cross product of two domains. So the builder, just go to the last point first, which is called the assembly operation, is where you take elements of domain A and elements of domain B, A and B, and make pairs of them. So as you make them as a pair, as a doublet or a tuple of size 2, then that doublet is an element of A cross B, the Cartesian product. So this is called the assembly operation, the builder operation. Similarly, given an element in the product domain, I can disassemble. What do I mean by disassembly? By disassembly, I mean I can either access the first component, or I can take out the second component. You have seen this kind of these notions significantly in lambda calculus earlier from the very beginning. So I can have a first function, this assembly operation, which takes A cross B and produces A, which gives me, given any AB pair, it gives me A. So first AB is A, similarly second AB is B, right? So in product domain, we have one assembly operator and two disassembly operator. Now this can be generalized to product domains of any number of domains. So A1, A2, AN. So then the builder is an n tuple, which represents an element in this product domain. And using the subscript, because this is an ordered tuple, so using the subscript, I can generalize the disassembly operation in 10 n different disassembly operation, where I write the tuple a down arrow indicating taking out from the tuple and the index value I. So A1, A2, AN, down arrow I, where I necessarily have to be between 1 and n, otherwise this operation is not defined, is AI. So first is basically down arrow 1, second disassembly operation is basically down arrow 2, but this in general is what can be done. Okay. So this is about the product domain. Then we have the sum domain. Sum domain is a disjoint union builder. We have seen it very extensively in terms of the type system, that we can actually take two different domains and make a union of that, so that in the union, at any instance, a value in that union could be a value of either domain A or of domain B, and they could be completely unrelated domains. So we did quite extensive study of that. We saw how to, how does it relate to union in C, and how it can be kind of implemented in terms of C or C++ and so on. And that tells us that the basic point to note here is I need a tag. I need a type tag. Whether the type tag is explicit as in C, or it is implicit, it could be implicit as in C++, but I need a type tag. So if I say A and B are two sum domains that two domains that we are making sum of, then in the classical representation, it will be represented as every element will be represented as an ordered pair, where the first in the pair is the type label. So say I'm using 0 to mean the first one, and then the element A. So this pair tells me that the sum domain element injected is of type A, because I have a 0, or I can have 1B, where this type tag 1 tells me that this is an element coming from domain B. Right? So the associated operations of builder is injection, as we have seen. So we have, just a little different notation, but it's the same concept, that I can take an element in A and inject it as an element in the sum domain. The function is called in A, which takes an A, gives me an A plus B sum. So in A necessarily is 0A. It puts a type tag on that element and puts it in the domain. Similarly, in B, injecting an element of the second domain type is in B is 1B. It puts the type tag of the second domain, which is 1, and puts it in the sum. So these are the associated builder operations. So type tags that the assembly operations place into their arguments are put to good use by the disassembly operation. So the type tags are given. So when I do disassembly, and we saw the disassembly earlier in terms of cases. So we say here, we use a function is A, which is basically the disassembly. So what is A does, given an L value D in the sum domain, is A will check what is the type tag. If the type tag is A, type tag is 0, that is domain A, then it takes out the associated value as the value of is A x. Otherwise, it does not do anything. Similarly, is B y will check if the type tag in D is 1, then it matches, then it concludes that the value is of type B and takes out that associated value as y. So if we have, it's kind of if we think that fx has a value e1 and gy has a value e2, then you can say that f has to be a function from a to c and g has to be a function from b to c. So is a function from a to c, which is whatever happens with that value x in the expression e, and gx or is b is a function from b to c. And naturally, so this whole thing represents a value in c. You remember the kind of baselines that we had discussed, that in terms of cases the resultant type has to be the same. Of course, otherwise this is not semantically consistent. So this is the disassembly operation for the sum type of domains, right? So we have product type of domains, sum type of domains. In sum type of domain, the following so in sum type of domain, the following will hold. If in A, cases of in A of this, if I write, that is, if I've injected a value of domain A and then we do this, then necessarily this will hold, is a x will hold. So the value will be f applied to A. So that which means that x here that you have taken out is replaced for A in E1. I'm sorry, A is replaced for x in E1, and that is what you'll get. So it is fx fa. Similarly, if I have done in B, and write the rest of the same expression, then the result will be GB. So this is precisely, and some of arbitrary number of domains can be built. We have seen that how to do this, and we can have A1 plus A2 plus AN to stand for a disjoint union of domains. Right? So this is what gives me the basic semantic algebra. That is where we have the semantic domains and we have their associated operations. So that algebra will tell us what this domain can actually do. Right? And we'll typically use this notation at the bottom of slide 45, E1 giving E2 or E3, which is called a choice function. So where E1 is a Boolean. So if E1 is true, then the value is E2. If E1 is false, the value is E3. Right? We'll just use this notation. Okay. Now, as an example, let me show you the semantic algebra for a domain which is rational. So I call it the domain rat. I mean, just to make sure that it does not get confused with anything else that we write, we are writing an underscore to mean that it is a semantic domain, defining a semantic algebra. So what is that? How is it built? It is built from two predefined domains Z. Right? So we have two predefined domains. So you have used a cross product builder, that is, we'll have a pair of natural numbers, a pair of integers, that is what we say. And then we have lifted the domain. So which means that it will also have a lifted value, right? Which means that it will also have a undefined or no value in the representation. Right? Now the first operation is how to actually make a rat. So you do make rat, which has to take a pair of values in the integer domain. So Z cross Z or Z maps to Z, and that gives you a rational number number in the domain rat. So Z cross Z or Z maps Z gives you rat. Now, in terms of lambda, what does it mean? It means that I have two elements from Z, P and Q. If P is equal to if Q is equal to 0, this is a choice function. If Q is equal to 0, then it is the bottom. Because obviously you cannot have a rational number where your denominator is 0. So you have no value. So that is how your lifted concept is being used. So if it is q is 0, then it's a bottom, and bottom is representable here because I have a lifted domain. Or it is the pair PQ. Right? Otherwise, it can be represented. We are not immediately taking care of the fact that GCD has to be 1 and so on. We can bring in those, but just keeping things simple. So another operation, add rat. So what will add rat do? We'll take a pair of rats and give you a rat. So this is mapping. So in lambda, I have a rat P1 Q1. I have another rat P2 Q2. And then that gives me a rat P1 Q2 plus P2 Q1 numerator, and Q1 into Q2 is the denominator. Right? Very simple. We are not doing LCM and all that, just to keep things simple. Naturally, there's a possibility that any one or both of these rational numbers are undefined. Right? So add-rat operation will check both of its arguments for definedness before it can perform the addition of the two fractions. Right? We'll see this concept more and more. This is called a strict application of the function, where you check before you apply the function, where you check whether your operands are actually valid. Right? Here, obviously, here we assume that operation, the add-rat performs that and gives you this only if both the input rats are valid. That is, they are not bottom. If any one of them or both of them are bottom, then we will try to interpret that this result is a bottom. Right? So if you are trying to add 2 by 0 plus 3 by 2, then 2 by 0 is bottom. So what you get is a bottom. Right? That's kind of. Similarly, I can have multiply, which has its lambda expression. You can define, subtract, divide, all of that. But this is just to show you how the domain can be represented. There is a example in terms of how you write it in Haskell. You know Haskell, so I'll leave it to you to read and understand this code. Okay, so this is kind of the domains that we have. Now, based on them, we can define complete semantic algebra. So let me just show you 1-2 initial examples. So let's say the semantic algebra of natural numbers. The first component of that semantic algebra is the domain, and then you have a set of operations. So it's a natural number, nat, which is a set of natural numbers. I need assembly operations, builders, assembly operations. So I have this set of operations 0, 1, 2. So what 0 does, it gives you the natural number 0. What 1 does gives you the natural number 1. So this is kind of a very interesting way of looking at constants, that you don't say that these are the constants, but you have a set of constant functions. Right? You call every function and you get a constant. Right? So there are infinite such operations. And then you have binary operators. So obviously these functions 0, 1, 2, and so on, they are zero-arity operators because they don't take anything. Just you call 1 and you will get the constant numeral 1. Then you have plus, which takes a pair of natural numbers, gives you a natural number, and so on. So this is the basic primitive domain of natural numbers. Now, certainly, we will have certain semantic rules for them. For example, x minus y, we have a subtract, right? And we are doing this in natural numbers, which means we cannot allow negative numbers, right? So if x is less than y, then it is 0. Right. So negative numbers, if the result happens to be negative, we define it to be 0. Right. So this is the definition of minus. I mean, it's not whether it is valid or not, you cannot question, because this is how we are defining it. Similarly, 6 divided by 2 is 3. 7 divided by 2 is 3, which is, you know what happens if you do integer division in C. 7 divide 0 is error. 2 plus error is error. So we need to handle this as no value or error. It is a choice. We might want to just use another element called error and represent these as error, or we can simply represent this as bottom as well. And so error is not always included in a primitive domain, and therefore when we include that, we will talk about it. So this gives you a basic idea of the semantic algebra of natural numbers. We can have a semantic algebra of truth values. So TR, the basic primitive domain is B. So you have two builder operations, true and false, which give you the truth value true and truth value false. You have a unary operator not, that is logical negation. You have a binary operator or, which is logical disjunction, inclusive disjunction. And you have a choice function, which is TR cross D gives you D, where D is some previously defined domain, some other previously defined domain, some other algebra. So which says that if the first component is TR, which is a truth value, if it is true, you take the first choice. If it is false, you take the second choice. So true of M or N is M, false of M or N is N. So this is a choice function. So this is your domain of truth values. So you can easily, evaluate, for example, not true is false, not false is true. So this is here. So the value of this expression is false, right? It says. So once we have defined the truth values domain, then we can extend the natural number domain further. For example, we were just having plus, minus, times, and divide. Now you can have equals. We can compare two natural numbers and say it gives a truth value less than, greater than, right? So we can have a more rich natural number semantic domain using the truth value domain. So we can write things like that, equals 1 plus 3. 1 plus 3 will give you 4. So 4 equals 4 is true. Not of that is false. So it comes here. 5 times 2 is 10. Less than 0 is false, right? So you get that. So this is what you have in the natural number domain. You can have a string domain. Naturally, we are just introducing. I mean, I know it's a little boring to go through these definitions, but without these, unless we are empowered with these, we cannot have really big real life example. So we have strings which are formed from the elements of C, the set of basic common set of characters, and it includes an error string. So we are specifically saying that there will be a string available called error, right? So not using the common concept of bottom. Okay. Now, what are the operations? A, B, C, I mean, all characters are strings. If you call A, it gives you a string containing A. If you call B, it gives you a string containing B, and so on. Then you have an empty string. Then you have an error string, right? Then you have different operators. Concatenation. You can concat two strings and get a string, which you can put them one after the other. You can get the length of a string to nat, and you can get a substring. Substring is you given a string and two natural numbers. you start from the position that is the first natural number and take as many elements as are there from that position as given in the second natural number. Right. So start at the position, take out so many, and then get a substring. That is the result. So substring ABC 1, 2, you start at position 1, which is A, take two elements AB. So this is AB. Substring ABC 1, 4, you start here, take four elements, does not exist. So the result is error. Substring ABC 6, 2, you start at position 6, does not exist, is an error. Concatenating error with any string is error. Concatenating any string with error is error. Length of error is 0, and so on. Right. So that gives you the basic string domain. Right. Then you have a very special domain, which is called the unit domain. Unit domain contains only one element and only one operation, that is the builder. So this is how you write it: a pair of parentheses, which gives you this unit element. So this is kind of a degenerate algebra, but theoretically it is very important because I mean, this is equivalent of the model of void kind of. So if I have to call a function which takes nothing, you can say that it takes this unit in is where the wherever you need a dummy argument, you can make use of this unit. It's an alternative form of error value also that we can see. So in some places we'll see that we'll make use of this. I think I'm almost out of time. So let me close here for now. Not a very good point in the discussion, but finally we have to respect time. So I just tried to introduce the denotational semantics. We closed on the discussion on semantic styles, and I just started introducing denotational semantics with its syntax and domains. And particularly as a build up to this, what we need is the knowledge of some of the common semantic algebras, and we started discussing on that in terms of having primitive domains, having compound domains, and having lifted domains, and starting to define algebra for natural number, for truth value, for string, for unit, and so on. So we have to do quite a bit more before we can get into the real examples. The unfortunate part is we are meeting after a long time after this, because this Wednesday you will have the test, and then next Monday and Wednesday you are on spring break, as I understand, 27 to 3rd. I think you are on spring break, so possibly so naturally we'll meet after that. So quite a long time we'll miss you. Okay, any question? Showman, is type system there?
No, sir.
Type system we have not. I did not say type system would be there. Did I? Type system is not there in the class test on Wednesday. This Wednesday, the type system is not there. Okay.
Hello, sir.
Yes, please.
So do we just have only two topics?
Only two topics in the sense I
like the ones covered after the first class test. Those are in the syllabus, or the previous class test is also in the syllabus?
see. I mean, this is a vacuously wrong question, because without lambda calculus syntax, can you do anything else?
Yes.
Right. So,
okay.
but if you ask that, are you going to check specifically on the lambda calculus syntax, like we were saying that, well, given a open lambda expression, can you parenthesize this properly, which was more a syntax question, right? No,
Sir, my
obviously,
question is more
obviously
like
we will not ask those kind of the questions. Will be based on the understanding of the previous two modules, right?
Mhm.
That was done after class test one. So to be specific, class test one was on. Uh, so this is on typed lambda calculus and lambda in C++, right, Shoman?
Yes, sir.
Okay. So I think that answers the question. So we will specifically have questions checking your understanding on these two, right?
Yeah,
So
just I just wanted to ask whether I need to revise the Haskell and Lisp concepts.
mm, you might,
Okay.
but the idea will not be to directly check them. See, the difficulty is these are all developing concepts, right? So in context of some question, a reference can happen to an earlier part, right? These are two different things as whether we are specifically focused on, like when we are setting questions on Haskell, the idea was to see if you know Haskell. But in reference to, well, what kind of typing Haskell is using, in reference to that, it goes. So that kind of. But the focus will be obviously on these two modules, right?
Okay, sir.
Okay. Thank you then very much. Wish you all the best for your test, and see you on Wednesday. The details will be sent out by Showman at a proper time. Bye.